The next family of series we look at is called the P-series, and they come with their own convergence test. So recall our two main goals in this chapter. I give you a series and you have to answer this question. First, does it converge or diverge? And then second, if yes, it converges, can we calculate its sum? For the P-series family, there's a very simple test to answer this question, but this is not possible, so we don't worry about calculating a sum. If we need to use a useful P-series, a converging P-series, if we actually have to use it, then we will just take as many terms as we need. We can't calculate a sum that it approaches. All right, here, this is a family. The name is P-series, and here are three examples of P-series. So you may want to pause the video, look at them, and try to figure out what they have in common. How could you write this as a form? Right? Put the index above each one, like 1, 2, 3, and you'll see that this one is of the form 1 over the square root of n, or 1 over n to the 1/2. The next one, put the index over it, 1, 2, 3. Oh, that's easy. This is of the form 1 over n, or 1 over n to the 1. This series is so well studied, it has a particular name. This is the harmonic series, and it was in your lab. So that's the harmonic series. You should know its name. It's exactly that. It's the series that's 1 over n, starting with n equals 1. And then finally, our last series, if you want to pause the video and write the sigma notation for this one, of course it's 1 over n squared, okay, which we also saw in the lab. So the general form of this series, if you look at these three, write it, 1 over n to the p, where p is a number larger than 0. P stands for positive number. Notice it's not positive integer. It's really easy to slip and say, oh, p stands for positive integer. That's very easy to do. It's not. Right there, there's a 1/2. And p could be 0.0856. It could be anything as long as it's greater than 0. You can think about why wouldn't p be less than 0 if you put a negative number here. Why would that be silly? Because it would flip up to the top and it would be n to the positive number. So p will never be negative in this form. And so that's the form for this family. All right, it's easy when you're first starting to confuse this with the geometric series because it seems like something to the something. So I put up specific example of each one and the general form of the terms. Look at these for a minute and notice what the difference is. Notice the difference at where the n is, the variable, the index, the thing that changes with each term. Here in the geometric series, the base is a constant that's the same in every term. It's always 1/2. And n, the variable, is in the exponent. That's why you could also call this an exponential series. That would actually be a better name for it. In the P-series, the n is in the base. It's always 1 over n, but the n, the variable, is in the base, and that changes with every term, and it's the exponent that stays the same with every term. So we'll repeat that. If the base stays the same, and the variable is in the exponent, that's an exponential series, or geometric. The variable is in the exponent. If the variable is in the base, and that changes, but the exponent stays the same, that's a P-series, 1 over n to the p. P will be the same for every term in the series. Here, p is 2. All right, here's the convergence test for P-series. First, a little note. You cannot just look at the term shrinking to 0 and say, oh, the terms shrink to 0, therefore it converges. That's not a test. In fact, every P-series passes that nth term test. Just by the nature, look at these. Think of n getting bigger and bigger and bigger for all three of these. The terms shrink towards 0. The terms approach 0 in every P-series as n gets bigger and bigger. So every P-series will pass the nth term test. And what does that tell you? What does it tell you if a series passes the nth term test? It tells you nothing. That's the TSA agent looking at a passenger about to board the plane and seeing no gun. Right? That tells you really nothing about the passenger. The passenger could still have some kind of concealed weapon. All right, so here is the test. You look at P. And the dividing line is p equals 1, as we've kind of seen before. If p is less than or equal to 1, then something happens. And if p is greater than 1, then something happens. And the colors kind of give it away, but if you want to pause and write what goes in each blank, and you may be recognizing where you've seen this before, if p is less than or equal to 1, then the series diverges. If p is greater than 1, then the series converges. So right away that tells you the harmonic series diverges. That's where p was equal to 1, that important historical series. All right, let's look at why this is the case. Well, there's a convergence test that you're not learning this year. It's in your book. I recommend that you read about it. It's very simple. It has been on the AP test in the past. It's normally part of the curriculum, but not this year. That's called the integral test. And it basically says that if you construct an integral like this, the integral doesn't give you the actual value of the sum of the series, but the integral does the same thing as the series, which means if the integral diverges, this corresponding series will diverge. And if the integral converges, the corresponding integral will converge. I won't give you any problems on this test, but it's helpful to look at it because it's such a simple test and it's very useful. All right, let's look at these integrals, these improper integrals from earlier in the year. And just think about, this will be on the test. Improper integrals will be on the AP test this year. So you're kind of 80% of the way there to understanding the integral test. So look at these improper integrals from earlier in the year and think about how we solved them. We looked at the antiderivative of this, that's x to the 1/2, and I don't care about the coefficients or anything. I'm just looking at what it does as x gets bigger and bigger and bigger. So x to the 1/2 as x gets bigger and bigger and bigger, all right, that's bad. That diverges. That gets bigger without bound. For this one, if you take the antiderivative, you get, of course, natural log of x. As x gets bigger and bigger, that also gets bigger and bigger and bigger, and that also diverges. Now look at this one. If you do the antiderivative of this, you get negative 1 over x. As x gets bigger and bigger and bigger, well, that approaches 0, so that's okay. That's not an exploding function increasing without bound, so this one converges. And by looking at this and thinking about it, you can see where the dividing line is. The dividing line is if p here was less than 1, and here was equal to 1. So if that's the case, the integral diverges. And this would be true. This would work for anything where p is greater than 1. Well, the same exact thing applies to the p series. And if you think about it, it makes a lot of sense. An integral is really a summation. Replace the x's with the letter n. And that's the basis of the integral test that you don't really have to know. But replace the x's with the letter n and you see the similarity to a series. A sum beginning with n equals 1, let n get bigger and bigger and bigger, 1 over n squared. Let's sum them all up. Okay, if the integral converges, the p series will converge. And if the integral diverges, the corresponding p series will diverge. So that's the background so you can connect with what you did earlier in the year and what you do have to know for the AP test. If you just wanted to memorize the test for the p series, there it is. Okay? But you notice it's kind of the reverse of the geometric series where it was bad for r to be bigger than 1 and good for r to be less than 1. So if you're just trying to memorize things without understanding, you can get your wires crossed. I recommend for both geometric and p series, you really think about why the test is what it is. Okay, here's an example for our last note. And this example is one of the tougher ones. It's like one of the tougher problems in the book. You look at this series, say I just give you this on a test, or you see it on the AP test, and you're asked, does it converge or diverge? And you look at it and say, I don't even know what kind of series it is. I'm looking at it, I feel stuck. We'll start going through the test. First, does it pass the nth term test? Does it look like the terms are getting smaller and smaller and smaller? And yes, they definitely are. You're taking the fifth root of 16, then the fifth root of something bigger, and the fifth root of something even bigger. So the terms are shrinking to 0, passes that test, so we need another test. So next you might look at it and say, well, is it a geometric series? And if you remember, the way we find out if something's a geometric series and determine the base r at the same time is to divide successive terms and see if we always get the same answer when we divide. So we divide this term by 1, we divide this by that, we divide this by that, and you don't get the same answer at all. So no, it's not geometric. All right, so we try p-series, and it looks like this is, we'll put an index above each term. Put the index above each term, 1, 2, 3, 4. Now this is starting to look promising. 1 plus 2, 381, 4, 256. So in this problem, you'll be expected to spot that pattern. You're expected to think of the index increasing by 1, match up and see, 2, 16. Okay, so that's 1 over 2 to the 4th, and then take the 5th root, plus 1 over 3 to the 4th, and take the 5th root, plus, you can see where this is going, 1 over 4 to the 4th, and take the 5th root. So this is a p-series, 1 over n to the p. And you can see from looking at this, see what's the same in every term. That's the p. The exponent's the same in every term, not the base. The base keeps changing by 1. The exponent's the same in every term. That's p, the exponent. It's a positive number. P equals 4/5, which is, we do our test, that's less than or equal to 1. It's less than 1. Therefore, what does this series do? It diverges.